Hello, my name is Fu Yixue, and thank you so much for inviting me to talk about quantitative echoplanar time resolved imaging. And I'm sorry that I couldn't join you in person, so I'm recording now from Boston and will provide this video. And I hope you could enjoy the talk and also enjoy the session. And if you have any questions or comments, please contact me at my email address or my Twitter. And okay, let's get started. In this talk, I'll first introduce what is EPTI, how it works, and why should we use it, and then I'll talk about EPTI's further development and applications for quantitative imaging, including in MR relaxometry, myelin water imaging, diffusion MRI, and multi-echo functional MRI, which will be followed by discussion and summary. EPTI was developed to address the limitations of EPI, such as distortion and blurring. So let's first see why EPI has those limitations and the ways to address them. EPI is a widely used acquisition method that can produce a 2D image in a single excitation. And during EPI acquisition, the different phase encoding lines are acquired at different time points, spaced at a time interval of around 1 millisecond of an echo spacing. And so the EPI acquisition shows as a diagonal line in the phase encoding and time domain. The image is then formed by an inverse 2D Fourier transform of these phase encoding lines. However, during the EPI readout, there's accumulated phase due to field inhomogeneity that can lead to image distortion. There's signal decay across the readout that can lead to image blurring, and only limited number of echoes can be acquired due to the long readout before the signal decays away. To reduce the distortion and blurring, we can use parallel imaging that undersamples in the K-space and reduce the effective time interval between the neighboring data and therefore achieve shorter readout length. And it shows in the KT space as a steeper line correspond to less phase and signal decay, and therefore resulting less distortion and blurring. We can go to higher acceleration in the K-space to achieve a much steeper line in the KT space. However, a high acceleration can lead to noise amplifications, so the image will have less distortion but low SNR and more artifacts. Multi-shot EPI is an alternative method that uses a few shots to acquire the K-space. Each shot will only sample a part of K-space to reduce the effective echo spacing. And this can be combined with parallel imaging to achieve a steep line in the KT space. But it still cannot eliminate distortion, and there's potential shot-to-shot phase variation artifacts. And now we know that the general idea is that if we can get a steeper and steeper line in the KT space, we can get less and less distortion and blurring. To quickly summarize, EPI has distortion and blurring because it generates an image from K-space samples evolving across time with accumulated imperfections. Parallel imaging or multi-shot acquisition can mitigate these problems but cannot fully address it. Next, I will talk about how EPTI can fully address these problems by recognizing the strong spatiotemporal correlation of the data and replace the conventional EPI image formation and resolve multi-echo images without any distortion and blurring. Now let's take a look back at the KT space. If we can fully sample all the data in the KT space, and at each column, all the phase encoding lines are sampled at the same time with the exact same B0 phase and signal magnitude. So we can take each column out to generate an image without any distortion and blurring. We can also get multi-contrast images with a small t increment of an echo spacing. However, this requires hundreds of excitation, leading to impractically long acquisition time. So how to efficiently sample the KT space? We want to design an acquisition method that can sample the KT space fast and efficiently using small number of shots, and also preserve the high sampling and readout efficiency of EPI with minimal dead time and short time interval or echo spacing. And finally, we want to apply only small gradient blips to minimize the eddy current changes. So EPTI achieves all these by exploiting the spatiotemporal correlation within the readout. It samples in the KT space with high undersampling using a spatiotemporal encoding pattern so that the neighboring data are spaced close in time with high temporal correlation and also complementary along the phase encoding direction to better take advantage of the spatial information provided by the multi-channel coils. And this strong temporal and spatial correlation will allow the undersampled data point in the KT space to be easily recovered. And in addition, EPTI can be combined with SMS by extending the spatiotemporal encoding to KZ together with multi-band excitation to achieve shorter TR. The spatiotemporal encoding pattern can be sampled using a multi-shot acquisition, and each shot covers a segment of the KT space with a zigzag trajectory that requires only small gradient blips and leads to minimal dead time and eddy current changes. And for example, we've demonstrated sub-millimeter resolution at 0.9 millimeter using a 3-shot EPTI. And an optimized spatiotemporal encoding pattern with further reduced dead time and higher spatiotemporal correlation can achieve single-shot acquisition for resolution around 1 to 3 millimeter. To reconstruct the KT space, a grapple-like reconstruction was originally used. A kernel that contains coil sensitivity and B0 information can be applied across the KYT space to recover missing data point. Now, a subsys approach is used to improve the reconstruction conditioning, which take advantage of signal evolution priors and extract a number of subsys spaces that can accurately represent the signal evolution across the echoes. And here I'm showing a spin echo signal evolution as an example. And then by estimating the coefficient of the subsys spaces instead of all individual multi-echo images, we can reconstruct multi-echo data with reduced number of unknowns and improved reconstruction conditioning. Now, after reconstructing the KT space, a time series of distortion and blurring-free multi-contrast images at small t increment can be generated and can closely track the signal evolution, in this case, a T2 star decay. And compare with the conventional EPI with distortion and compressed structures, EPTI achieves similar structure integrity compared to the distortion-free reference. The multi-contrast images provided by EPTI can provide signal evolution information across TEs. Here are 2 example images from 2 slices that moves across 112 echo images in a gradient echo and spin echo acquisition. We can see the defacing area that spreads out in the gradient echo and then gradually recover in the spin echo as expected. EPTI also allows for high acquisition efficiency by using continuous readout to fill out any dead time between the pulses. And here's an example of how we are playing these small gradient blips to acquire the EPTI trajectory in the KYT space. So in summary, EPI generates an image from K-space samples evolving across time with accumulated imperfections, while EPTI recognizes the strong spatial-temporal correlation of the data within the readout during the image encoding process, and exploits this correlation to replace the conventional EPI image formation and results multi-echo images from the fully recovered spatial-temporal data, and therefore making the images free from the effects of these imperfections. And this can turn a liability, which is the evolution of the MR signal with time, which yields geometric distortion and signal blurring, into an asset, providing a variety of benefits and unique features, including distortion and blurring-free images, multi-echo images with a wide range of TEs, and also the high readout efficiency. EPTI can also be applied for non-Cartesian sampling as well. For example, in propeller echoplanar time resolved imaging with dynamic encoding or peptide, instead of sampling the KY segment, peptide samples the propeller blade with in-plane rotation in the KY and KX plane to provide self-navigation and motion correction. Circular echoplanar time resolved imaging incorporates circular K-space coverage and maximum ramp sampling into EPTI and reduce the readout length to about 75% of the original. It shows the multi-contrast images and the T2 star map acquired by a 3-shot circular EPTI. The EPTI concept of resolving multi-contrast images within the readout can also apply to spiral trajectory. For example, spiral crisscrossing echoplanar time resolved imaging, or ACE-EPTI, samples a series of complementary spirals within the readout and resolves the readout to obtain multi-contrast images. This can address the blurring for spiral and obtain multi-contrast images with self-navigation for motion correction. Next, I also want to briefly review other reconstruction methods for APTI in addition to the grappa-based and subsys reconstruction. For example, a model-based reconstruction was developed for APTI that take advantage of the signal model and directly estimate the quantitative parameters for improved conditioning at high accelerations. Another study explored the low rankness across EPTI multi-echo data after the grappa reconstruction to increase the data SNR. There are also machine learning-based reconstruction methods developed for EPTI. For example, this work uses autoencoder and decoder to achieve a more compact representation of the signal evolution to reduce the number of unknowns. And another study used zero-shot spatiotemporal deep generative priors to improve the constraint reconstruction. So now we've discussed what is EPTI and how it works, what's the advantage of it, and why should we use it, and also some extensions of EPTI. Next, I'll talk about EPTI's further development and applications for quantitative imaging, and I'll start with MR relaxometry. Using a 2D EPTI in a gradient echo and spin echo acquisition, we can achieve whole brain fast quantitative mapping in 28 seconds. And here shows the multi-contrast images and also the quantitative parameters, including T2, T2 star, proton density, B0, tissue phase, and SWI that's acquired all in the 28 seconds. To further increase the efficiency of EPTI for MR relaxometry, a 3D EPTI technique was developed. Similar to 2D EPTI, it uses continuous readout and resolve multi-contrast images within the continuous EPTI readout that can closely track the signal evolution. The spatiotemporal encoding was extended from 2D to 3D with complementary sampling along both phase encoding direction and partition encoding direction. And in this way, we can take better advantage of the coil sensitivity along both directions, and together with the use of the temporal correlation within readout, a high acceleration factor of 80 can be achieved. The 3D PTI readout is then applied to a pulse sequence designed to be sensitized to different quantitative parameters, including T1, T2, and T2 star. And on top of the 3D PTI readout with high acceleration, a new sampling strategy was developed on top of this to sample different k-space locations between different readouts. And it forms a radio block sampling to create incoherent aliasing that can be removed based on compressed sensing theory. In addition to the temporal correlation within the readout, it also uses the temporal correlation between readouts, and this provides additional acceleration capability. The integration of continuous readout and novel spatiotemporal encoding within and between readouts provide unique highly undersampled datasets, which will be reconstructed by taking advantage of the signal evolution priors, and also the coil sensitivity and B0 information from calibration data, and a subsys reconstruction was used to reconstruct thousands of time-resolved multi-contrast images from which we can get quantitative parameter maps. 3D PTI achieved fast 3 minutes whole brain scan at 1 mm isotropic resolution. It resolved thousands of multi-contrast images with varying T1, T2, and T2 star contrast. And from these images, we can get high-quality whole brain quantitative maps, including T1, T2, and T2 star, proton density, and B1 at 1 mm isotropic resolution, all in just 3 minutes. And the high acquisition efficiency allows for improved spatial resolution within acceptable scan time. For example, 0.7 mm isotropic resolution was acquired within only 9 minutes. The high spatial resolution allows for better evaluation of cortical depth profiles using the simultaneously acquired T1, T2, T2 star maps. And here shows the quantitative maps at different cortical depths. And we can see there are characteristic low-value regions consistent with highly myelinated regions such as the motor and sensory cortex. We can also look at the value changes as a function of a cortical depth in different ROIs, which are also repeatable across scans and subjects. Finally, synthetic images with useful clinical contrast can be synthesized and obtained within the same scan. While 3D EPTI achieves significantly reduced scan time and therefore higher motion robustness, we want to further increase this motion robustness and correct for motion for each TR. So a 3D EPTI with 4D navigator acquisition was developed, and the navigator was acquired with minimal cost of SNR and efficiency of the overall acquisition. It can effectively correct for motion by tracking the motion and the B0 change for each TR, and achieves a good image quality and consistent value compared with the motion-free reference. So to summarize, while we talk about EPTI recognizes the strong spatial-temporal correlation of the data within the continuous readout, therefore achieves high acceleration capability and high readout efficiency for multi-contrast imaging, and therefore leading to high efficiency for MR relaxometry. 3D EPTI further increases the acceleration capability by integrating a within readout scheme that extends the spatial-temporal EPTI encoding from 2D to 3D for controlled aliasing, and a between readout scheme with a radio block encoding strategy that explores the data correlation between the readouts in a longer time scale, and remove the incoherent aliasing based on the compressed sensing theory. And the 3D EPTI readouts are combined with the pulse sequence that are sensitized to T1, T2, T2 star parameters to achieve fast multi-parametric mapping. And finally, a 3D EPTI sequence with 4D navigator can track both motion and visual changes to improve the motion robustness. So next, I'll talk about EPTI for Myelin water imaging. While Myelin imaging is important to study the brain in both health and disease, MR-based Myelin water imaging can separate the Myelin water content based on its shorter relaxation times using multi-compartment modeling. However, this will need for high SNR multi-contrast acquisition that can lead to long scan time and very limited resolution. EPTI can be used to improve the efficiency of multi-contrast acquisition for Myelin water imaging, and here a variable flip-bungle EPTI acquisition was developed to obtain multi-flip-bungle and multi-echo data sets to provide the multi-contrast images with T1 and T2 star and frequency information for multi-compartment analysis. And it uses a 3D EPTI readout to resolve the multi-echo images and then acquire multiple flip-bungle with complementary sampling to improve the acquisition efficiency. To reconstruct the undersampled data and recover accurate signal evolution from multiple compartments, a multi-compartment model-informed subspace reconstruction is implemented. Specifically, a three-pool model with different T1, T2, and frequency is used here to simulate the complex signal evolution in the acquisition, and then to generate the subspace spaces that contains the multi-compartment signal evolution information to jointly reconstruct the multi-flip-bungle and multi-echo data, and therefore reduce the number of unknowns and improve the reconstruction conditioning. And variable flip-bungle EPTI achieves fast 5 minutes Myelin water imaging scan at 1.5 mm isotropic at 3T, which can be useful to move towards fast Myelin water imaging for clinical application. And here shows Myelin water fraction map with highly myelinated structures in the white matter. And at the same time, we can get the T2 and T2 star and T1 map for different compartment pools. And with its high efficiency, BFA EPTI also achieves high spatial resolution at 600 micron isotropic resolution at 70. And we can see the parameter maps with high spatial resolution and highly detailed structures. To sum up, EPTI provides efficient multi-contrast acquisition that's highly suitable for multi-compartment modeling analysis. And here specifically, VFA-EPTI was developed to acquire multi-echo, multi-flip bundle gradient echo acquisition using the 3D EPTI readout. And a joint substitute construction that incorporates a multi-compartment information or signal model was used to reconstruct the data across the multi-echo and multi-flip bundle. And an extended complex 3-compartment model was applied for the Myelin water fraction estimation. So the high sampling efficiency of EPTI allows for fast Myelin water imaging and sub-millimeter Myelin water imaging to study the cortical Myelin architecture. So next, I want to talk about the application of EPTI for diffusion MRI. Diffusion MRI is a widely used tool to study tissue structure and connectivity. However, there's a few challenges for diffusion MRI acquisition, including the geometric distortion due to the API readout, and also the low image SNR due to the use of the diffusion gradient. And using EPTI, we can achieve distortion-free, motion robust, with significant SNR efficiency gain to enable high spatial resolution diffusion MRI at a mesoscale level, and also efficient microstructure imaging. So if we look at the conventional spin echo EPI acquisition, it combines all the long readout data to form one image. And in addition to the distorted image, it also results in dead time before the 180 and a long echo time. So ACE-EPTI achieves minimal TE by starting the readout right at the spin echo point and avoid the dead time between the 90 and 180. And this is possible due to the time resolve feature of the EPTI readout. And in addition, the readout length is flexible in such time resolving approach because it's no longer determined by the resolution. And we can use optimal readout length to achieve optimized SNR efficiency. And together with the TE reduction, it can result in about 30% higher SNR efficiency. Moreover, instead of the uniform spatiotemporal encoding EPTI, ACE-EPTI uses a 3-shot encoding pattern that provides a self-navigation capability for phase estimation and correction, and the phase estimation can be done using the central K-space signal of each shot. And the encoding was also designed to have complementary KY sampling to take advantage of the coil, and also only small KY blips are needed to reduce the echo spacing and the eddy current changes. So to recover the highly undersampled KT data, a phase-corrected substitute construction is used for ACE-EPTI to resolve the distortion-free multi-echo diffusion images. And in this reconstruction, the eddy current induced odd even echo phase difference, the shot-to-shot phase variations, and also the dynamic B0 changes are incorporated to improve the image quality and remove potential phase artifacts. ACE-EPTI provides SNR-efficient distortion-free diffusion MRI with multi-echo information for diffusion relaxometry, and the distortion-free feature of EPTI can also get rid of the dynamic distortions caused by eddy current across different diffusion directions. And here shows the FA maps at different TEs obtained by ACE-EPTI as multi-echo data, and also the T2 star can be fitted for both non-diffusion and diffusion-weighted images by using the multi-echo images. Recently, a Romer EPTI technique was developed to achieve distortion-free diffusion MRI with significantly higher SNR efficiency and motion robustness. It integrates an SNR-efficient motion robust fixed slice acquisition with rotating wheel encoding along slice and readout direction, and also the distortion-free EPTI encoding that samples in the phase encoding and time or echo time domain. Romer EPTI achieves high SNR efficiency, high motion robustness, and distortion-free diffusion MRI, and also with multi-echo imaging. The high SNR efficiency enables ROMER-EPTI to achieve in vivo mesoscale diffusion MRI. And here are example data at 500 micron isotropic resolution acquired in vivo at 3T with high quality and no distortion or slight boundary artifact. And we can see the highly detailed structures. And at 7T, it achieves even higher resolution, and we can see the highly detailed structures on the mean DWI. And you can see more details in abstract 541. And here shows the FA map of the two data set. And at this high resolution, more detailed structures and connectivity can be reviewed. And in another abstract 690, ROMER-EPTI can also provide high SNR diffusion MRI for microstructure imaging. For example, it provides significant SNR gain for high B-value diffusion MRI compared to the conventional EPI acquisition. It also provides efficient time-dependent diffusion MRI, and using the data acquired within a short scan, clear time dependency was observed. To summarize, build on the work of ACE-EPTI, ROMER-EPTI achieves efficient diffusion MRI that's free from distortion and T2 and T2 star blurring, and has high SNR efficiency by using the flexible EPTI readout that allows for minimal TE and optimized readout length. And ROMER-EPTI also uses rotating view thick slice acquisition combined with SMS to provide additional high SNR efficiency gain. It's robust to motion and phase because the spatiotemporal APTI encoding pattern was designed with self-navigation, and a motion-aware reconstruction was applied, and also the distortion-free readout is robust to blurring due to motion-induced geometric changes. Finally, the multi-echo images provided by ROMER-EPTI can be used for diffusion axometry and provide more information to study tissue microstructure as well. So finally, I want to briefly talk about EPTI's application in functional MRI. The multi-echo information and the fitted T2 star and S0 can be useful for improving functional MRI sensitivity as well. And specifically, we can look at the T-dependent information and to differentiate the signal noise by looking at whether the functional changes is more T2 star related or S0 related, and then remove the noise component to improve the functional MRI sensitivity. And using EPTI, there's also other benefit to improve the functional sensitivity, including its distortion-free, which is both for static and dynamic distortion. And also the early TEs can be used to recover signal voids or dropout and recover the functional sensitivity in those challenging areas as well. And also the optimized readout length can help increase the TSNR and the CNR efficiency. EPTI can also resolve varying contrast weightings across the readout and therefore provide pure contrast that can improve the functional specificity. For example, the spin echo EPTI acquisition can be used to resolve the different contrasts across the spin echo readout and obtain the pure spin echo contrast where it achieves the highest specificity. And in addition to T2 bolt, it can also be applied to other functional contrasts such as FASO or ASL to improve the specificity by removing unwanted contrast contaminations. So we've reviewed APTI's application in MR relaxometry, Myelin water imaging, diffusion MRI, and also multi-echo functional MRI. To summarize, EPTI is a readout technique that can be applied to different pulse sequences to obtain different contrasts or quantitative parameters. We've demonstrated EPTI's applications in diffusion and functional MRI, MR relaxometry, and Myelin water imaging. It provides resolved multi-echo multi-contrast imaging, which is suitable for tracking signal evolution for quantitative mapping and multi-compartment modeling. It provides highly efficient sampling with minimal dead time and high acceleration capability, which means it can achieve higher SNR efficiency and shorter scan time. EPTI images are free from geometric distortion and T2 or T2 star blurring, which addresses EPI's limitations, especially in diffusion functional MRI applications where EPI is the standard acquisition. APTI encoding can provide self-navigation to track and correct motion or bezier changes to improve the motion robustness, and future directions include new reconstruction approaches that can further improve its reconstruction conditioning and acceleration capability, and also new hardware advances such as better coils, bezier shimming, and gradient can also help improve EPTI's performance. Finally, we're excited to share that we will be disseminating EPTI soon, so stay tuned and see more details on our website shown here. For questions and comments, please contact me at my email address or my Twitter. And we also want to share that we're hiring with postdoc positions available, so please contact me if you're interested. I invite you to see our other related talks, including Romer EPTI for mesoscale diffusion MRI at both 3T and 7T, and also Romer EPTI for high SNR microstructure imaging and diffusion MRI. Thank you so much for your attention.